Welcome to our deep dive into large language models. We're going to be taking a look at the paper S1, Simple Test Time Scaling, which introduces a new way to improve how these models reason.
The paper really focuses on this idea of test time scaling. This is sort of a different way of thinking about how to build bigger and better language models.
So instead of just giving a language model tons of data, what if we change the way it thinks during the testing phase?
That's the idea. It's all about improving how the model uses its resources when it's actually working on a problem.
What I find really cool about this deep dive is that the researchers have created an open source model called S132B, and they've also created a data set to go with it called S1K.
That open source part is really important because it makes this research much more transparent compared to those closed models from companies like OpenAI, so it encourages collaboration and sharing within the research community.
So when it comes to test time scaling, the folks behind this paper found that having really good quality reasoning data is absolutely crucial.
They actually created this unique S1K dataset with only 1,000 questions, and it turns out this small, carefully designed set is more effective than using hundreds of thousands of examples.
Tell me more about how they put together this S1K dataset. It sounds fascinating.
It's a pretty rigorous process. They started with a massive pool of 59,000 questions and solutions. These questions came from all sorts of fields like math, physics, computer science, you name it, even standardized tests and brain teasers.
Wow, that's a huge range of questions.
They actually used Google's Gemini Flash Thinking API to generate solutions for every single one of those 59,000 questions. So that gives them a really solid foundation of high-quality problems with verified answers.
Makes sense. So they make sure that they were starting with good questions and solutions. How do they narrow it down from there?
Well, they used two language models of different sizes to get rid of the questions that were too easy.
So they kept only the questions that really required the model to think hard.
Exactly. And then they also filtered for diversity. They wanted to make sure the questions represented different subjects, and they gave preference to questions that had longer reasoning paths.
So the end result is a compact but incredibly powerful data set that pushes the boundaries of what language models can reason about.
Precisely. It's like a concentrated dose of reasoning challenges.
That's a great way to put it.
Yeah.
So now we get to the S132B model itself.
This model is a fine-tuned version of an existing model called Qwen 2.532B Instruct, and they trained it on this special S1K dataset we talked about.
And this is where things get really impressive. The training process was incredibly efficient.
It only took them 26 minutes on 16 NVIDIA H100 GPUs, which is a testament to how effective a smaller, well-curated dataset can be.
So they've got this model trained on this high-quality reasoning data, and then they put it to the test on some seriously challenging benchmarks.
We're talking AME 24, which is a very competitive math exam for high school students, Math 500, which is a collection of really tough math problems, and then there's GPQA Diamond, which is a set of PhD-level science questions even experts struggled with.
Those are some serious tests. So how did S132B stack up against the competition?
It outperformed other models that were trained on much larger datasets by a significant margin.
So this really highlights the power of their sample-efficient approach. They achieve better results with less data by focusing on quality and strategic selection.
Now let's dive into the heart of their test time scaling method. It's called budget forcing.
What exactly is budget forcing?
In simple terms, it's about controlling how long the model is allowed to think before it has to give an answer.
Almost like setting a timer for the model to ponder the problem.
They found that by slowly increasing this allowed thinking time, the model's accuracy on benchmarks like AME 24 significantly improved.
So the more time the model had to think, the better it performed.
And here's an interesting tidbit they discovered, that just adding the word wait to the model's current line of reasoning encourages it to think a little bit longer, which led to further gains in accuracy.
It's as if that simple word, wait, prompts the model to pause and reflect, leading to more insightful solutions.
It's a fascinating finding that suggests even subtle interventions can significantly influence how LLMs reason.
Now, in addition to budget forcing, the researchers also explored some other test time scaling methods, including conditional length control and rejection sampling.
Conditional length control attempts to explicitly tell the model how long to think, either in terms of tokens or steps, but it seems to have some limitations in terms of precision.
And rejection sampling generates multiple solutions and then chooses the one that best fits a given compute budget. So it's kind of like exploring various options and picking the best one.
While these methods have their merits, budget forcing stood out as more controllable and more effective overall.
So the researchers have really made a strong case for budget forcing as a powerful technique for test time scaling.
Now, one important point they make is that the sequential scaling, where the model thinks step by step, it eventually hits a limit.
What causes that limit?
It has to do with the way language models work. They have a fixed context window, which is essentially the amount of information they can hold in their memory at any given time.
So as the model's reasoning chain gets longer, it might bump up against the limits of its memory capacity.
Exactly. So to address this, they suggest incorporating parallel scalar techniques like majority voting or tree search, using a reward model they call rebase.
These techniques sound pretty sophisticated. Can you break them down a bit?
Majority voting is pretty straightforward. You generate multiple solutions and pick the most frequent one as the final answer. It's like a democratic vote among the model's different outputs.
And tree search using rebase.
This is a bit more complex. You use a reward model to evaluate the different reasoning steps and then guide the model towards the most promising branches of a reasoning tree. So it's more like strategically exploring a maze.
So in essence, parallel scaling allows the model to explore multiple lines of reasoning simultaneously.
Precisely. And this can be a game changer for models with limited context windows.
So by combining parallel and sequential scaling techniques, we could potentially unlock even greater reasoning power in LLMs.
It's a promising direction for future research, and it really highlights the need to think outside the box when it comes to optimizing these models.
This has been a fascinating look at test time scaling and the S132B model. It's clear that this research is opening up new avenues for enhancing LLM reasoning capabilities. And with the open source nature of their work, they're encouraging wider participation and collaboration in this exciting field.
Now let's take a deeper look at some of the specific ablations and experiments presented in the paper.
That sounds like a great place to pick up in part 2.
The researchers analyzed a specific question from the AME24 benchmark, where the model initially generated a correct answer when rejection sampling was used to limit the thinking time to 4,000 tokens. When the limit was increased to 8,000 tokens, the model produced an incorrect answer.
A closer examination of the generated reasoning traces shows that in the shorter generation, the model directly arrived at the correct approach in the longer generation. It engaged in extensive backtracking and self-questioning, which ultimately led it down an incorrect path.
This example provides evidence to support their hypothesis that shorter generations often reflect instances where the model was on the right track from the beginning. Longer generations could indicate that the model struggled to find the right approach. And this suggests that simply generating more outputs doesn't always guarantee better solutions. Sometimes a more focused and efficient approach is more effective.
Now let's shift our attention to the discussion and related work section of the paper, where the researchers connect their findings to the broader landscape of LLM research.
One of the key findings is the impressive sample efficiency of their approach. They show that with just 1,000 carefully selected examples, a reasoning model can achieve performance comparable to models trained on much larger datasets, like OpenAI's O1 preview model.
This challenges the common belief that bigger is always better when it comes to LLMs. It suggests that focusing on the quality and strategic selection of training data can be just as important, if not more so, than simply increasing the dataset size.
The researchers believe that this remarkable sample efficiency stems from the fact that LLMs are already exposed to vast amounts of reasoning data during their initial pre-training phase, which usually involves trillions of tokens. They suggest that fine-tuning essentially activates the reasoning abilities that are already present in the model, making it more adept at applying these skills to challenging problems.
This aligns with the superficial alignment hypothesis from the Lima paper, which proposes that a small set of high-quality examples can be enough to align a model's behavior with desired goals.
The paper also highlights the importance of constantly developing more challenging benchmarks to push the limits of LLM reasoning abilities. They reference several recent benchmarks, including Olympiad-level science competitions and problems designed to test higher-level cognitive skills.
These challenging benchmarks are essential for driving progress in the field. They provide a clear measure of how well LLMs can handle complex, real-world problems.
There are a number of strategies that researchers have been exploring to improve LLM reasoning performance. These include continuing training on specialized data sets related to specific domains like math or science, using synthetically generated data to expand training data sets, and developing specific training methods aimed at improving reasoning abilities.
The paper also mentions prompting-based methods like chain-of-thought prompting, which encourages the model to produce a step-by-step reasoning process before arriving at a final answer.
These various approaches highlight the dynamic and rapidly evolving nature of LLM research as the field strives to create models capable of tackling increasingly complex reasoning tasks.
Let's dive into the specific methods used for test time scaling. Starting with a deeper exploration of parallel scaling techniques, we briefly touched on this earlier. Parallel scaling involves running multiple computations independently. and then combining the results. Two prominent methods explored in the paper are majority voting and tree search using the rebase reward model.
Majority voting is quite straightforward. You generate multiple solutions and choose the most frequent one as the final answer. This is based on the idea that the most common answer is likely to be the correct one.
And tree search using rebase. How does that work?
Tree search with rebase is a bit more complex. It uses a reward model that evaluates individual reasoning steps and guides the model toward the most promising branches of a reasoning tree. This allows the model to explore multiple reasoning paths simultaneously, potentially finding solutions that would be difficult to achieve through a purely sequential process.
So the paper compares the performance of rebase to majority voting and sequential scaling on the AME24 benchmark. What were the findings?
Their findings show that rebase scales more effectively than both majority of voting and sequential scaling, achieving higher accuracy as the computational budget increases.
But does using rebase introduce any computational overhead?
It does require an additional forward pass through the reward model for each step, so there's a trade-off to consider. But the results suggest that parallel scaling methods like rebase have a great potential for pushing the boundaries of test time scaling and unlocking even more reasoning power in LLMs.
The paper also highlights a crucial observation, that sequential scaling, which depends on the model thinking step by step, eventually encounters limitations due to the fixed context window of the underlying language model. As the reasoning chain becomes longer, it can exceed the model's ability to hold all the necessary information in its working memory, leading to a decline in performance.
This limitation is particularly important for complex reasoning tasks that involve many steps, or a lot of information. Parallel scaling methods, like rebase, offer a way to address this problem by exploring multiple reasoning paths at the same time. They can effectively work around the constraints of a fixed context window.
This emphasizes the importance of considering both sequential and parallel scaling techniques when designing test time scaling methods. Finding the right balance between the two could be the key to unlocking the full potential of LLMs.
The paper concludes by highlighting the potential impact of their work on both research and society. They argue that LLMs with strong reasoning abilities can enhance human productivity in various applications, from aiding in complex decision-making to accelerating scientific discoveries.
They also stress the importance of transparency and open collaboration in LLM research by making their model S132B and dataset S1K publicly available. They aim to foster innovation and accelerate progress in the field.
This open approach encourages researchers to build upon their work and collectively work towards more powerful and beneficial AI systems. Now, let's delve into the supplementary materials provided in the appendix to gain a deeper understanding of the technical aspects and design choices that support their research.
The appendix starts by providing more details about the training process for the S132B model. It includes a comprehensive overview of the hyperparameters used during fine-tuning, such as batch size learning rate optimizer and weight decay settings. It also highlights the use of bfloat16 precision, which helps reduce memory usage and speed up training.
The researchers also included visualizations of the training dynamics, including graphs showing the training loss, learning rate schedule, and gradient norm over time. These visualizations offer valuable insights into the stability and convergence of the training process, demonstrating that the training loss consistently decreased and the learning rate followed a well-designed schedule.
The appendix then shifts focus to a specific ablation study that explores the impact of the training sequence length on the model's performance, as we discussed earlier. The researchers discovered that training with a longer sequence length resulted in shorter reasoning traces during testing and more efficient inference.
They conducted an experiment comparing two models trained with different sequence lengths, 4,096 and 32,768 tokens. The model trained with the longer sequence length performed better on all three benchmarks and exhibited shorter reasoning traces, leading to faster inference.
This finding emphasizes the importance of considering the structure and completeness of the training data, not just the quantity, when developing LLM for reasoning tasks.
The next section of the appendix provides a detailed breakdown of how the S1K dataset was created, starting with the composition of the initial pool of 59,000 questions and the different sources they came from.
These sources include Numina, a collection of math problems from websites, math, a data set of competition math problems. Olympic Arena, featuring questions from various Olympiads covering different scientific fields. Omnimath, another set of competition-level math problems. And AG Evil, which includes problems from standardized tests like the SAT and LSAT.
They also included questions from various other sources like crossword puzzles, code problems, from coding competitions, and even university-level qualifying exams in subjects like statistics. This diverse range of sources ensures that the S1K dataset represents a broad spectrum of reasoning challenges requiring different cognitive skills and knowledge across various domains.
The appendix also includes a table that shows the average thinking length measured in tokens for each source. This highlights the differences in complexity across different types of problems.
For example, questions from Numina and AIM tend to have longer thinking lengths, indicating that they are more difficult and require more reasoning steps. Questions from sources like XWord and Seville have shorter thinking lengths, suggesting they are less complex in terms of reasoning.
This detailed analysis of thinking length provides valuable insights into the characteristics of different problem sources, and this information was used to carefully select and balance the questions within the S1K dataset.
The appendix then delves into the final selection process, used to narrow down the initial 59,000 questions to the 1,000 questions that make up the S1K dataset.
This multi-stage process ensures the quality, difficulty, and diversity of the final set of questions.
They started by using Google's Gemini Flash Thinking API to generate solutions for all 59,000 questions. Then they used two language models of different sizes to eliminate questions that were too easy. They also manually checked the solutions for correctness and clarity.
And how did they ensure diversity in the final dataset?
They developed a two-stage sampling algorithm that prioritized questions from AIM GPQA and Math 500 benchmarks, which are known for their high-quality trains. Then they sampled from the remaining questions using a weighted approach that favored questions with longer reasoning traces. This ensured a balanced representation of different domains while also giving more weight to questions requiring more extensive reasoning.
The appendix provides a detailed explanation of the sampling algorithm they used. This level of transparency is important because it allows other researchers to understand and potentially replicate their data curation process, which helps ensure the reproducibility and reliability of the research.
The researchers included several examples of questions and solutions from the S1K dataset to illustrate the effectiveness of their data curation process. These examples show the challenging nature of the selected problems and the intricate steps needed to find the right answers.
One example comes from the S1 prob subset, which features questions from Stanford University statistics. PhD qualifying exams. This particular problem involves proving that two conditional expectations are equal under certain conditions. The solution requires a good understanding of advanced probability concepts like martingales and stopping times.
This example highlights how the dataset focuses on problems that go beyond just computational skills, requiring deep conceptual understanding and the ability to apply abstract mathematical reasoning.
Another example comes from the S1 teasers subset, which includes brain teasers typically used in quantitative trading interviews. This problem asks to calculate the expected number of coin flips Alice makes, given that Bob flips his coin more times than Alice. The solution involves combining probabilistic reasoning and combinatorial analysis.
This example shows how the dataset emphasizes problems that demand creative problem-solving and out-of-the-box thinking in addition to mathematical proficiency.
They also provide an example from the astronomy section of Olympic Arena, where the model is tasked with calculating the surface temperature of the sun if it were the same size, but had the same power output per unit volume as a human.
Solving this requires applying the Stefan-Boltzmann law and carefully handling units and ratios to arrive at an answer that is approximately 50,000 Kelvin.
These diverse examples give us a glimpse into the intellectual depth and breadth of the S1K dataset, demonstrating its ability to challenge and train LLMs for complex, multi-step reasoning across different disciplines.
Now let's shift our focus to exploring alternative approaches to controlling test time compute. The appendix starts by examining token conditional control, where they tried to directly tell the model how many tokens to use in its reasoning process. They provide visualizations of how token and step instructions were incorporated into the model's input during training.
As we discussed earlier, they found that token conditional control was not very effective. The model often struggled to stay within the specified token limits.
They included tables showing how the model performed on the AME24 benchmark when given different token instructions. These tables show that the model frequently exceeded the target token count, and even when forced to stop at the limit, it often didn't achieve good accuracy.
So these findings suggest that simply telling the model how many tokens to use is not a reliable way to control its reasoning process.
To try and address this limitation, they experimented with step conditional control, where they divided the reasoning traces into steps using double new lines as natural separators, and told the model to think for a certain number of steps instead of tokens.
So instead of controlling the number of individual words, they controlled the number of reasoning steps the model could take.
This approach was somewhat more successful. The model tended to follow the step limits better than the token limits, But the control was still not perfect, and there was no guarantee that the model would always stay within the specified range.
So it seems that while using steps as a unit of control is a step in the right direction, LLMs still need further development to achieve truly precise control over their thinking process.
The researchers were curious about OpenAI's reasoning effort API parameter, which offers settings like low, medium, and high followed. They hypothesized that OpenAI might be implicitly controlling thinking time by making subtle changes to the prompt or system instructions.
So to test this idea, they experimented with class conditional control using different prompts to encourage either short or long thinking.
They found that the prompts did have some effect on thinking time. The long thinking prompts generally led to longer reasoning traces, but the control was not very precise and did not always lead to better results.
For instance, on the AME24 benchmark, the short thinking prompt actually resulted in slightly higher accuracy than the default prompt, even though it led to less thinking time.
This suggests that simply encouraging the model to think longer does not always guarantee better performance, and highlights the complex relationship between thinking time accuracy and the specific reasoning task at hand.
So it seems that while prompt engineering can influence thinking time, it's not a reliable way to achieve fine-grained control over test time compute.
The last part of the appendix focuses on a detailed analysis of rejection sampling, which, as we discussed before, involves generating multiple solutions and choosing the one that fits a given compute budget. Surprisingly, they found an inverse scaling trend with this method.
What do you mean by an inverse scaling trend?
They found that shorter generations tended to be more accurate than longer ones, which was unexpected.
That's counterintuitive. You would think that giving the model more time to think would lead to better results.
To understand this unexpected finding, they examined a specific AME24 question where the model's performance actually got worse when they increased the allowed thinking time.
What happened in this specific case?
When the thinking time was limited to 4,000 tokens, the model efficiently found the right approach and produced the correct answer. But when they increased the limit to 8,000 tokens, the model's reasoning became much more complex. It started backtracking, exploring irrelevant paths, and ended up with the wrong answer.
It sounds like the model got lost in its own thoughts.
That's a good way to put it. The researchers believe that this inverse scaling trend happens because shorter generations often represent situations where the model was on the right path from the beginning, while longer generations may indicate that the model was struggling to find the correct approach and made more mistakes along the way.
This highlights the importance of not only looking at the final answers, but also carefully examining the reasoning process to understand how LLMs arrive at their conclusions.
This research provides valuable insights into test time scaling in large language models. The researchers introduced budget forcing as a new and effective method for controlling how long an LLM thinks, explored the potential of parallel scaling techniques like majority voting and rebase to address the limitations of sequential reasoning, and emphasized the importance of careful data curation and the need for more sophisticated evaluation metrics.
Their decision to make their model and dataset publicly available is commendable. It encourages more research and collaboration in this rapidly advancing field. Their work represents a significant step towards developing more efficient and powerful reasoning models.
Now let's move on to part 3, where we'll delve into specific ablations and experiments conducted by the researchers to further understand the factors contributing to the success of their approach.
The researchers conducted a series of ablations to understand how well token conditional control worked as a way to manage the compute resources used during testing. They tried to directly tell the model the exact number of tokens to use for its reasoning process. Visualizations in the paper show how token and step instructions were incorporated into the model's input during training.
However, the results showed that token conditional control wasn't very effective. The model had trouble consistently staying within the specified token limits.
So even when they tried to set strict limits on the number of tokens the model could use, it didn't always work out as planned.
That's right. They presented tables that show how the model behaved on the AME24 benchmark when given different token instructions, and it frequently went over the intended token count.
And even when it was forced to stop at the limit, it often didn't give accurate answers.
This tells us that simply telling the model how many tokens to use isn't a reliable way to control its reasoning. LLMs don't have a strong way of keeping track of and managing their token use during the generation process.
To try and get around this, they experimented with step conditional control. Instead of trying to manage individual tokens, they divided the reasoning process into steps, using double new lines as natural breaks.
So they instructed the model to think for a specific number of steps instead of a specific number of tokens.
That makes sense. Seems like a more manageable way to control the model's thinking.
And the results were somewhat better. The model tended to follow the step limits more closely than the token limits, but it still wasn't perfect.
It still had trouble staying within the boundaries they set.
Exactly. The control wasn't precise enough to guarantee that the model would always stay within the limits they set. This suggests that while using steps is a more intuitive and potentially more controllable way to manage the reasoning process, LLMs need to be further developed to have truly precise control over how they think.
Now I'm curious about how OpenAI controls the amount of compute used during testing their reasoning effort. API parameter offers different settings like low, medium, and high motion. The researchers thought OpenAI might be subtly changing the prompts or system instructions to indirectly control thinking time.
They tested this idea by using class conditional control with separate prompts designed to encourage either short or long thinking.
So one prompt was geared towards quick and efficient thinking, and the other was designed to make the model think more thoroughly.
That's the idea, and their findings showed that these prompts did have some influence on the model's thinking time. The long thinking prompt generally led to longer reasoning chains, but the control wasn't precise and didn't always result in better accuracy.
It's interesting that on the AME24 benchmark, the short thinking prompt actually led to slightly better accuracy than the default prompt, even though it resulted in a shorter thinking time.
That's an important point. It shows that just encouraging the model to think for a longer time doesn't necessarily lead to better results. There's a complex interplay between thinking time accuracy and the specific task at hand.
So it seems that while prompt engineering can have some effect on how long a model thinks, it's not a reliable way to achieve fine-grained control over test-time compute resources.
To have more precise and predictable control, we'll likely need to develop more sophisticated mechanisms that allow LLMs to effectively monitor and manage their own reasoning processes.
The appendix wraps up with a detailed analysis of rejection sampling, where you generate multiple solutions and pick the one that fits within a set compute budget, as we discussed earlier. The research found a surprising inverse scaling trend with this method. Shorter generations tended to be more accurate than longer ones.
This was an unexpected finding. It challenges the assumption that giving a model more time to think will always lead to better outcomes.
The researchers investigated this further by looking closely at a specific AME24 question. In this case, the model's performance actually got worse when they gave it more time to think.
When the thinking time was limited to 4,000 tokens, the model was able to find the correct solution efficiently, but when they increased the limit to 8,000 tokens, the model's reasoning got much more complex, and it ultimately ended up with the wrong answer.
So it seems like in some cases, giving the model more time to think can actually lead it down the wrong path.
That's the idea the researchers suggest, that shorter generations often happen when the model is on the right track from the beginning, while longer generations might happen when the model struggles to find the correct approach and makes more errors along the way.
This highlights the importance of analyzing not just the final answer, but also the steps the model took to get there. By understanding the model's reasoning process, we can better identify areas for improvement.
This research sheds light on the complex and sometimes unpredictable nature of how LLMs reason out. It challenges our assumptions about the relationship between thinking time and accuracy, and emphasizes the importance of carefully analyzing both the model's final outputs and its internal reasoning process. This deeper understanding is crucial for developing more effective strategies to improve LLM performance.
The S1, Simple Test Time Scaling paper, is a valuable contribution to the field. It introduces new ideas for controlling how much thinking an LLM does during the testing phase, and it highlights the potential benefits and challenges of different scaling methods.
Their findings show that the way we train and evaluate these models plays a crucial role in how well they perform, and by making their model and data available to others, they're fostering collaboration and pushing the field forward.
This deep dive into test time scaling in the S1 model has been fascinating. It's clear that the ability to control and optimize the reasoning process of LLMs is crucial for unlocking their full potential. And as these models become more powerful and widely used, research like this will play a vital role in shaping a future where AI can effectively augment human intelligence.
Until next time, keep exploring.